Dear students, let us start with corollary. If f is Riemann integrable on closed interval ab, g is Riemann integrable on closed interval ab, and f of x is less than or equal to g of x, almost every point in closed interval ab, then integration from a to b f is less than or equal to integration from a to b g. Proof. Here we have given f is Riemann integrable on closed interval ab and g is Riemann integrable on closed interval ab. Also we have given f of x is less than or equal to g of x almost every point in closed interval ab. Then we have to show that integration from a to b f is less than or equal to integration from a to b g. Okay. Since f is Riemann integrable on closed interval ab, that implies minus f is also Riemann integrable on closed interval ab. Why this is? Because it is properties of Riemann integrable. If f is Riemann integrable on closed interval ab, then lambda into f is Riemann integrable on closed interval ab. Here lambda is -1. Okay. And g is Riemann integrable on closed interval ab. Also, we have given f of x is less than or equal to g of x almost everywhere in closed interval ab. That is, 0 is less than or equal to g of x minus f of x almost everywhere in closed interval ab. But by previous lemma, integration from a to b, g of x minus f of x is greater than or equal to 0. Why this is? What is previous lemma? Previous lemma is if f is Riemann integrable on closed interval ab, f is greater than or 0 almost everywhere in closed interval ab, then what happens? Integration from a to b, f is greater than or equal to 0. So therefore integration from, now this implies integration from a to b g of x plus integration from a to b minus f of x, which is greater than or equal to 0. Therefore integration from a to b g of x minus integration from a to b f of x. This is by property of Riemann integration. This is also by the properties of Riemann integration. Okay. Therefore integration from a to b g of x is greater than or equal to integration from f of x. Okay. Therefore integration from a to b f is less than or equal to integration from a to b g. Hence we have proved which we want to prove. Okay. Very simple corollary. Now we will see one more corollary. If f is Riemann integrable on closed interval ab, then mod f is Riemann integrable on closed interval ab, and modulus of integration from a to b f is less than or equal to integration from a to b mod f. Okay. Proof. See here, since we have given mod f is Riemann integrable on closed interval ab, therefore by existence of Riemann integral integral, therefore by existence of Riemann integral, f is continuous almost everywhere. F is continuous almost everywhere in closed interval AB. Mod f is Riemann integrable on closed interval AB. Therefore, by existence of Riemann integral, f is continuous almost everywhere in closed interval AB. But we know that mod f is continuous. Mod f is continuous as f is continuous. As f is continuous. Mod f is therefore mod f is continuous almost everywhere in closed interval AB. Therefore, here f is Riemann integrable. That's why f is continuous. So, mod f is continuous as f is continuous. Therefore, mod f is continuous almost everywhere in closed interval AB. Therefore, again by existence of Riemann integral, mod f is Riemann integrable on closed interval AB. Now we have to prove that modulus of integration from a to b f is less than or equal to integration from a to b mod f. Okay. Now, to show that modulus of integration from a to b modulus of, or here say we have to show that. We have to show that. Okay. We know that f of x is always less than or equal to mod of f of x. Obviously, this mod f of x can be written as mod f of x. Here x is belongs to x is belongs to open interval AB. Okay. Therefore, f of x is less than or equal to mod f of x is continuous almost everywhere in closed interval AB. Here f of x is less than or equal to mod f of x. Therefore, this is continuous almost everywhere in closed interval AB, because our f and mod f are continuous almost everywhere in closed interval AB. Okay. Therefore, by previous corollary, what happens? Here is previous corollary. Integration from a to b f is less than or equal to integration from a to b mod f. Okay, call this equation 1. Also, since minus f of x minus mod of f of x is less minus f of x is less than or equal to mod of f of x, which is equals to mod f of x for all x's belongs to closed interval AB. Okay, this is therefore minus f of x is less than or equal to mod f of x, this is mod of f of x almost everywhere in closed interval AB. Again, by previous corollary we get minus, here is minus integration from a to b f is less than or equal to integration from a to b mod f. If we here we get integration from a to b minus f is less than or equal to integration from a to b mod f. If we multiply by this inequality by minus 1, we will get integration from a to b is greater than or equal to integration from a to b minus mod f. Suppose call this equation 2. By 1 and 2 we get what we get integration from a to b minus mod f is less than or equal to integration from a to b f, which is less than or equal to integration from a to b mod f. Therefore modulus of integration from a to b mod f is less than or equal to integration a to b f. Here is mod of integration from a to b f less than or equal to integration from this is not modulus of f. Okay, integration from a to b mod f. Let us take one remark. If f is continuous on closed interval 0 1, then integration from 0 to 1 f of x dx is equals to limit n tends to infinity 1 by n summation k runs from 1 to n f of k by n. Okay, this is the remark. Suppose this is 1. Second, limit n tends to infinity 1 by n summation k runs from 1 to infinity f of k by n is equals to integration from 0 to 1 f. Here put this k by n is equals to or equivalent to x and 1 by n equivalent to dx. Okay, now see problem based on this remark. First example is evaluate limit n tends to infinity 1 by n summation 1 by n square plus 2 by n square plus and so on plus n by n square. Okay, plus and so on, n by n square. Here we have to find this limit. Okay, solution: limit n tends to infinity 1 by n square plus 2 by n square plus and so on plus n by n square is nothing but limit n tends to infinity. Write general series for this series. See here, 1 by n is common. Okay, this is 1, 2, so on. Here we write as this is series k runs from 1 to n, k by n bracket square. Okay, what is our remark tell? It tells that put k by n is equivalent to x and 1 by n is equivalent to dx. Okay, so here this 1 by n remains. So therefore we have limit n tends to infinity 1 by n square plus and so on plus n by n square is equal to limit n tends to infinity. Here k by n is equivalent to, this is, sorry, here is not limit. Limit is equivalent to integration, which is integration from 0 to 1. 1 by k by n is nothing but x. Here k by n square, so here x square, and 1 by n is dx. Take integration, which is x cube upon 3, which is equal to 1 by 3. Limit of this series is 1 by 3. Okay, now take one more example. Suppose example 2. Evaluate 1 by n e raised to 3 by n plus e raised to 6 by n plus and so on up to e raised to 3n by n. Okay, this is, which is equals to series e raised to 3 by 2 plus and so on plus e raised to 3n by n. Here is 3 by n. E raised to 3 by 2 plus and so on e raised to 3n by n. Okay, this series is equivalent to limit n tends to infinity 1 by n series k runs from 1 to infinity f of, here actually this series is, this is the multiple of 3, so 3k by n. This series is equivalent to 3k by n. Okay, put k by n is equivalent to x and 1 by n is equivalent to dx. Therefore limit n tends to infinity series e raised to 3 by n plus and so on e raised to 3n by n is equals to integration from 0 to 1 e raised to, this k by n is x, so this is e raised to 3x into dx, which is equals to, take integration of this function e raised to 3x, integration of e raised to 3x is 3x upon 3 from limit 0 to 1. This is nothing but e raised to 3x upon, e raised to 3 upon 3 minus 1 upon 3. This is equals to e raised to 3 minus 1 upon 3. Okay. Let us take one example for homework. Evaluate limit n tends to infinity 1 by n a raised to 1 by n plus and so on plus a raised to n by n. Here a raised to 2 by n. Evaluate this limit. Okay. Again take one more example. Third, evaluate limit n tends to infinity 1 by n sin pi by n plus sin 2 pi by n plus and so on plus sin n pi by n. Okay, this is homework to you. Solve these two problems. Okay, we will stop here. Thank you.